Okay, here we would like to give a much more interesting, so not so trivial example of using L'Hopital's rule. And before we proceed, it's useful to note that we're going to use something in order to simplify our work. So recall that the limit as x tends to 0 of sine x over x is equal to 1. And one might say, where am I recalling this from? I mean, we haven't really seen it. Well, if you think about it, the limit as x tends to 0 of sine x over x is the same as the limit as x tends to 0 of sine x minus sine 0 of x minus 0, which is pretty much this quotient is what computes the derivative of the function sine at 0. So this should be the derivative of sine x at 0. Yes, but the derivative of sine is cosine, and cosine of 0 is 1. Okay, so in other words, we can argue that the limit of sine x over x is equal to 1. So this is a parenthetical note, and let's start working with our limit, which is certainly an indeterminacy because as x tends to 0, 1 over x squared tends to infinity, and same thing for 1 over sine square of x. So both of these things tend to infinity. So we have a different kind of indeterminacy, which is infinity over infinity. To apply L'Hopital's rule, we certainly need to form a quotient. So what we do is we clear denominators here. So we do sine square of x over sine square of x times x squared minus x squared over sine square of x times x squared. So we multiply and divide the first fraction by sine square of x, the second fraction by x squared, and we get the limit as x tends to 0 of sine square of x minus x squared over x squared, or sine square of x times x squared. And this is where we do a little trick to make our life easy, because the differentiations on the bottom as we start applying L'Hopital's rule are going to become very complicated. So we rewrite this as so we create, let's see, we pull the sine square of x in a new fraction that we create with this x squared. Of course, you will ask where this x squared came from. It doesn't really matter because we're going to also multiply by x squared. So now I hope you can see that these two things cancel each other. So in other words, there is the balance that we had before, and then what you have on the denominator is x squared times sine square of x, which was precisely what you had before. Okay, the only thing is that by writing it this way and remembering that sine of x over x tends to 1, now it's enough to turn our attention to this limit. And this is the trick that I was talking about before. So this is really the limit that we should be talking about. So this tends to 1, in other words, because it's 1 over sine of x over x all squared. So this tends to 1. And it suffices to compute the limit as x tends to 0 of sine square of x minus x squared over x to the fourth. that x to the fourth is x squared times x squared. And here you will see that we will need pretty much 4 applications of L'Hopital's rule. The differentiations are not that hard, neither on the top nor the bottom, but they have to be done carefully. So we will apply L'Hopital's rule four times. And we will also use a trigonometric identity to simplify things at some point. So let's see. So we start with the limit as x tends to 0 of the derivative of the top over the derivative of the bottom. And this will be the limit as x tends to 0 of what is the derivative of sine square of x? Think of sine square of x as sine of x all squared. That's what it is. So we use the chain rule. Think of sine x as y. The derivative of y squared is 2y times the derivative of what we designated as y minus 2x. And the derivative of x to the fourth is 4x cubed. And this is where I said that we might want to use a nice little identity. So we know that sine of 2x, or it is known, I should say, is equal to 2 sine x times cosine x. This will make our life a little easier. So let me rewrite this as limit as x tends to 0 of sine of 2x minus 2x over 4x cubed. And now we will use L'Hopital's rule a second time. So that will give us, so I will take the derivative of sine of 2x minus 2x over the derivative of 4x cubed, because simply this goes an indeterminacy 0 over 0 that we found before. So this will be the limit as x tends to 0 of cosine of 2x times 2 minus 2 over 12x squared. And now, what do we have? Plug in 0 again. What do you get? You get cosine of 0 is 1. So 2 times 1 minus 2, that's 0 on the top and 0 on the bottom. So again, this is an indeterminacy of the form 0 over 0. So we're going to apply L'Hopital's rule a third time. So we will take the derivative of cosine of 2x times 2. Let me put the 2 in front. Minus 2 over 12x squared, derivative of that. And this will be the limit as x tends to 0. Now, the derivative of cosine of 2x is, again, by the chain rule, negative sine of 2x. So we will get negative 2 sine of 2x times 2. And of course, the derivative of 2 is 0. And on the bottom, we get 24x. So there is a little bit of a cancellation here. So we get the limit as x tends to 0 of negative sine of 2x over 6x. And finally, again, this is a 0 over 0 indeterminacy. So we'll apply L'Hopital's rule for one last time. So we will get the derivative of minus sine of 2x over 6x derivative. So that's the limit as x tends to 0 of minus cosine of 2x times 2 over 6. And now things are pretty straightforward because we can plug in x equals 0. It's not an indeterminacy anymore. And that's negative 2 over 6. Cosine of 0 is cosine of 0 is 1, and this will give us negative 1/3. So eventually, after all these L'Hopital applications of L'Hopital's rule, 4 of them, we get that the limit as x tends to 0 of 1 over x squared minus 1 over sine square of x is equal to negative 1/3. And of course, one might ask here, why are we finding a negative number? What's the idea behind the negative number? Well, sine x in general is less than or equal to x. So since you put things on the denominator, sine square of x is less than 1 over x squared, which means that 1 over sine square of x is greater than 1 over x squared. So actually this quantity right here is greater than that, and it makes sense that we get a negative number. And that's all with this problem, a quite non-trivial application of L'Hopital's rule, or four of them for that matter, with the interesting trigonometric identity that we had here, and certainly the non-trivial initial step that allows us to simplify our limit. And that's all. Thanks for watching.